for the planets of the solar system. In particular, we'll focus on Earth and Venus. Very similar planets, yet very, very different climates. I kind of call it a tale of two planets. Greenhouse effect. Clearly, Earth is not alone in possessing greenhouse gases such as water vapor, carbon dioxide. Venus and Mars also are warmed substantially by the greenhouse effect. We shall now compute that effect. Mercury itself, you wouldn't expect there to be much warming because it doesn't have much of an atmosphere, so there's basically no greenhouse gases. So let's do the computation now. It's based on how much power the sun puts out, how much energy is absorbed by the planets. We can then compute the amount of energy that the planet would radiate, and that would then give an effective temperature. Fortunately, the greenhouse effect is real. Without it, the Earth would be horrendously cold. So, greenhouse effect is a good thing. Here's a view of the inner solar system. We have Mercury closest to the Sun, followed by Venus, Earth, and Mars. Venus and Earth are, within the same sort of range and distance. I mean, obviously Venus is closer. But let's now go ahead and compute the heating that Earth should experience. So here's the relationship of the Sun to the Earth. 1 astronomical unit is the distance. Corresponds to 500 light seconds. Another good number to know. And that's about 150 million kilometers. Now it all starts with the Sun. If the Sun is hot, the hotter it is, the hotter the planets will be. That's intuitively obvious. The surface of the Sun radiates that light at 6,000 degrees Kelvin. Let's assume we could analyze what's coming out of 1 square meter of the Sun. Well, it turns out that the black-body radiation formula gives a very simple expression. The total power coming out per unit area is sigma T to the 4th. Sigma is the Stefan-Boltzmann constant, the value is given there, and T is the temperature of the emitting body. So for the Sun, all we need to do is plug in the value of 6,000, do the multiplication, and we come out that the power that the Sun emits, per unit area, is 74 megawatts per meter squared. Just think about that for a second. Compare that to what a house consumes, and you will quickly see that in this case, 1 square meter of sun would essentially be enough to heat up a small city. It would be on the order of 20 to 30,000 houses that could be heated. Now let's compute the total amount of energy coming from the Sun. Well, that's the amount per unit area, sigma T to the 4th, times the surface area of the Sun. That's 4 pi r squared. Pretty simple. And with that, we can compute the total amount of energy. Now we can compute the amount of energy that's absorbed by the Earth. It's obviously proportional to the amount of energy the Sun is emitting, Ps emit, times basically the ratio of the surface area of the Earth divided by the surface area of the total distance the Earth's orbit covers, 4 pi d squared, is sort of a volume. And there's a reflectivity factor, 1 minus RLE. The emitted power of the Earth, of course, would be sigma T4 times the surface area of the Earth. So we have 3 equations. The power of the Sun that emits, the power that the Earth emits, and basically with those equations, and of course the power that the Earth receives. With those 3 equations, we can go ahead and solve for TE, the temperature of the Earth. And as you imagine, it's equal to the temperature of the Sun times some geometric factor, which is RS, the radius of the Sun, divided by 2 times the distance from the Sun to the Earth, times this reflectivity factor, 1 minus RLE. If the reflectivity factor is 1, you see that the temperature increases 0. So we have to balance these various things. Let's plug in the numbers for Earth. Earth has a reflectivity of about 0.3. The distance of the Sun to the Earth is 150 kilometers, and the radius of the Sun is about 700,000 kilometers. Plug in the numbers. What do we get? TE is equal to T Sun, 6,000 degrees Kelvin, times, when you solve it, you get this 0.048, that's the geometric factor, and then you get this 0.91, which is the reflectivity factor. Turns out that that is 262 degrees Kelvin. That's pretty cool, actually. That corresponds to about minus 10 degrees C or 14 degrees Fahrenheit. Room temperature is about 30 degrees warmer than that. So roughly, there's a difference in 30 degrees. What's going on there? We can do the same computation for how much the planet should be heated up by the sun. The only factor is the distance and the reflectivity. Remember, the size of the planet does not matter in this analysis. So what we're showing here are the distances for Mercury, Venus, and Mars. We can go ahead and plug in the numbers. Let's also, here's a table, includes the reflectivity for the 4 planets. Mercury is rather dark, so kind of a dark stony place. Low reflectivity, 0.12, whereas Venus is quite high. Earth, as you see, is about 0.3, Venus is 0.75. If we compute based on the reflectivity and the distance, this is the black body temperature of the planets respectively: 630, 239, 262, 215. Whoa, interesting. The Earth should actually be hotter than Venus because of Venus's high reflectivity. Well, it turns out measurements have been made, good measurements have been made. It turns out Venus is quite hot. It's 740 degrees Kelvin, in fact much hotter than just the computation based on the black body radiation. And Earth, like I said, is about 30 degrees Kelvin warmer. Even Mars experiences some pleasant warming due to what? It's really due to the greenhouse warming effect. These gases trap the heat, as we described in some of the previous videos. Venus has what's called a runaway greenhouse effect. I mean, it's just out of control. It's so hot, it's like an oven, 500 degrees Kelvin increase, whereas Earth's about 30 degrees Kelvin. Could the Earth someday become like a Venus? What's going on? Let's analyze this, okay? So what we're going to do now is basically I'm going to do more of a comparison. The extra warming is due to the greenhouse effect. We clearly know that, okay? Earth is warmed up 30 degrees Kelvin, Venus 500 degrees Kelvin. Venus has an atmosphere that is primarily made of carbon dioxide. I'm going to compare the 2 planets because there are some differences between the planets, but basically the key differentiator is greenhouse gases. CO2 traps that sunlight on Venus and it makes it a scorching temperature. It would melt solder on the surface of Venus. Totally inhabitable. Can the Earth get that way? We shall see. So basically, this is a summary of the analysis that we've gone through. What's happening? More sunlight, hotter, further away, cooler, higher reflectivity, cooler, more greenhouse gas, hotter. Those 4 factors are what dominates the temperature. So with that, I will leave it right now and say thank you. And I do want to get into a comparison of Venus and Earth in much more detail because it's a fascinating story.